All right, in this follow-up question, if an electron is placed on the surface of Earth with a charged source of positive 3 nanocoulombs located above the electron, how high above the electron would the source need to be in order for the electron to feel weightless? So interesting idea. So think about what's going to happen if you take any object and you set it on the surface of the Earth. Well, that object is going to be attracted by gravity to the Earth, right? That's our weight, right? We all have a weight. We accelerate downward at 9.8 meters per second squared. But what if we had this suction above us, right? This force that's pulling up on us like a source charge would do to a charged object on the surface of the Earth. Well, we would be lifted up to a point where we might even flow away from the surface. Well, at some point before we actually lift off, we would reach a point where we have no weight. We would not be accelerating downward. The fields effectively cancel. Right? So when I draw this one up, if we had Earth and we would have an electron right on the surface, there's our electron, and we would have some source that would be a positive 3 nanocoulombs. Now, it would have to be positive in order to pull upward on the electron. Let's make that source in red, and we'll do the Earth in blue just to get a really good visual of what's happening here. So there's a couple ways you can look at this. All right? Both those objects are going to exert forces on the electron. And if it's going to be weightless, then it's going to feel like it's not having any weight or any force on it. So one way to look at it would be to say, well, there must be a downward force of gravity that exactly matches the upward force of the electric field. Right? So for it to be weightless, that would have to be true. You also could look at it as the field strength. The electric field would have to match the gravitational field. Right? That would also be true. Right? So for it to be weightless, you could say one of two things. You could say that Fe is equal to Fg, or again, you can say the fields are equal. There's a field due to the electrostatic field, and there's an acceleration due to gravity there as well. Either way would work, and at some point, we're going to need to know, well, what is this distance in order to make that true? Let's plug in what we would have here. If I want the field, E is simply K, the charge of the source, and the distance from the source squared. And the acceleration due to gravity is big G, right, m over the distance to the center of the Earth squared. But we know we're on Earth, so we actually know that value. It's 9.8 meters per second squared. All right, so that's one way to do it. Now notice, if I wanted to find Fg, isn't Fg just mass of the electron times 9.8? And wouldn't Fe just be the charge of the electron times E? Right? And so it ends up not really mattering how we do it. Although, now that I mention it, I think mass and electron aren't the same thing, are they? So maybe I do need to use the actual forces. Right? Because those fields maybe act a little bit differently on a mass than a charge. So let's add that in there, right? So we have the charge of the electron. Also, let's use this equation. That's really what we need to look at. So let me throw the charge of the electron in here. And let's throw the mass of the electron in here as well. And now that's definitely true. Those two forces are equal, and now we're good to go. All right, so I think we might have gone astray if we stuck with just the fields, because the fields act differently on masses than they do with charges. So I think we're ready to roll now. So now I have K, I have the source charge, 3 nanocoulombs. I have the charge of an electron. I know the strength of the gravitational field. I know the mass of an electron. The only thing I don't know is the distance, and we're going to solve for it. Algebraically, I can rewrite this as K, Q source, Q electron, over, again, I can flip these two parts, over 9.8 times the mass of the electron. And that has to equal the distance squared, and then I can take the square root of both sides and solve for d. And so the distance d, when I plug in my values, is going to be the square root of 9 times 10 to the 9. The charge of the source is 3 times 10 to the negative 9. It's in nanocoulombs. The charge of the electron, 1.6 times 10 to the negative 19. All over 9.8, the field strength of gravity at the surface, times the mass of the electron that's reacting in the field. And when we get that, and if I did all the units right, I would get a distance in meters. So I'm going to pull up my calculator here. Unfortunately, I think I don't have my screen shared, so you can't see how I'm actually typing it in. But I'm going to be careful with my parentheses. I'm going to do 9 second e to the 9 times 3 second e to the negative 9 times 1.6 second e to the negative 19. I'm going to divide that, and I'm going to make sure I put parentheses around my denominator, 9.8 times 9.11 second e to the negative 31. Close my parentheses, hit enter, and then I need to remember to take the square root of my answer. I could have done that at the start and had more parentheses, but I get 695,616. So I get a distance of 695,616, and if I had everything in coulombs, meters per second, all that stuff, I should get meters. It's really crazy, right? Roughly 696 kilometers above the surface is where that source would have to be. It really gives you a sense of how strong that electric field is compared to gravity, right? 100 kilometers is roughly, I think 125 is like roughly the edge of space. So we're way out, maybe even close to the space station or beyond, is where that charge would have to be to lift that tiny little electron. So, again, I think you do got to stick with just looking at it as the forces, because those fields act a little bit differently. I don't think it would have worked the other way. But hopefully it gives you a pretty good example of what we're doing, how we can use Coulomb's law to solve a problem like this. All right, so I'm going to slide over and stop the video.